Are we back on here? Okay. Now, in soils, I actually have something on soils. You have moisture in soils, and it turns out you don't have a lot of soils in the Navy, but nonetheless, soil is important. So the Army has 15,000 storage tanks, at least when they did the study in 1991. They had 15,000 underground storage tanks in the U.S. Army for fuel and all kinds of other things. I guess the Navy has it on their bases too. But the Army owns more than the Navy. And so they did a big study at the Construction Engineering Research Labs out in Urbana-Champaign, Illinois. And they showed, oops, it's upside down. Here's a plot of the soil aggressiveness value, and I'll explain what that means in a little bit. But this is the corrosion potential of the soil versus the age of the leaking tank. This is 108 tanks. The quickest leaks were in 6 years, and typically some of these tanks have about an 1/8 inch thick wall. Some of them might be a 1/4 inch if it's a great big tank, you know, like you see it at an aviation depot or something. But a lot of their tanks are little small tanks of 500 or 1,000 gallons, and they might be an 1/8 of an inch thick. If we take our little thing up here and we say, gee, it started to leak in 6 years at an 1/8 of an inch wall, which is 125, that's 20 thousandths of an inch per year. Although, and it was an aggressive soil in these two, or these down here, but some of them last 30 years. And they've had some tanks last 40 years. Now last, what was it, December or last winter, we had, anybody from West Virginia? Anybody remember what happened in West Virginia? They shut down all the water because they had, this company had some chemicals that they stored for the part of the mine stuff. And it turns out the tank started leaking, and they got over a protective barrier into the city of Charleston water supply. Okay. Well, those old tanks were riveted tanks. Okay, they were from the 1940s. Someone might have thought that maybe they should have been inspected. Okay. And some of them are they're just pure rust on the bottom. Okay, so far as that goes. You know, that company is now basically bankrupt. The company that owns the tank, but the water authority is being sued because they're not bankrupt. So far as that goes. What is the aggressiveness index? Here it is. These are the basic characteristics. So we got the soil resistivity in ohms, and the higher the resistivity, the less aggressive. Okay, this is sort of like the megohms of water. If you can't transfer the electrical charge to have the chemical reaction, you know, to have a chemical reaction, you're transferring electrons from one atom to another. You've got to have an electrical circuit. So if the soil resistivity is low or is high, then you don't get corrosion. But if you have a very low soil resistivity, the soil pH, obviously, if you're very caustic, it turns out the Poor-Bay diagram tells you that the steel becomes sort of immune at high pH. But in a very acidic environment, the soil moisture, well, that's just part of the whole resistivity, the loop. Dry, it's great. If it's saturated with water, it's not as aggressive as high resistivity. Differential characteristics, so they had a regression formula that took some of these things into account, so you get the cross effect of some of these things. And then the sulfide content, okay? If you had sulfide, now this tends to be sulfide reducing bacteria. Okay, there's certain types of corrosion which we now call MIC, microbiologically induced corrosion. Which we really didn't recognize the first I ever heard about MIC was about 1979 or so. They had some MIC corrosion in a nuclear reactor, and these bugs were surviving 40,000 rad. Okay, so those who use it, a human would last for about 3 minutes with, I mean, it's just, they were replicating their DNA so fast, repairing their DNA. It's just incredible, okay? If you look at, I mean, these bugs were right there in one of the hottest parts of the reactor, and they had this little colony of bugs. They have to have something to eat, okay? So you have to look at it. But in this case, some bugs will reduce sulfur compounds, and that's what they eat, okay? Don't ask me, I'm not a biologist, but basically they call them SRBs, sulfur-reducing bacteria. And it wasn't something that we thought about in the corrosion literature until about 40, 45 years ago, when we saw this stuff in nuclear reactors. Now, you read a report on corrosion in a tank or something, and half the metallurgists in the world say, oh, it must be MIC, okay? So now everything is MIC, okay? In fact, people even have MIC. I had I can't remember the one I had. It was MIC on copper. Well, wait a second. Copper actually kills bugs. I mean, if you had a copper-hulled ship, in 1836, Sir Humphrey Davy made a copper-hulled ship for the British Navy to get rid of all the barnacles that would grow on there. Copper is something that kills organic things at fairly low concentrations. So copper is toxic. You shouldn't be eating lots of copper, but there's not enough copper in the copper water pipes. It doesn't corrode fast enough. They worry about the lead in the pipes from the solder. They've taken lead out of solder in Massachusetts in 1978. But copper is not a problem for that, but they put, if you could afford to have copper-lined boats, and they've had some boats down in the tropics where the barnacles and other things grow very rapidly, and you can almost justify, because within 1 year you can basically be dead in the water from the weight of the barnacles and the drag and whatnot. Now, none of you are old enough to know what the Navy used to use. Anybody ever heard of tributyl tin? Okay, well, back as recently as the early 90s, David Taylor in the 70s or 80s had come up with tributyl tin added to the paint, and this would kill any mollusk in the entire harbor. Okay, I mean, parts per billion or parts per trillion, and it would just wipe out all the mollusks in the and some of the fishermen in some of the harbors where they had the Navy ships were complaining to Congress, and so finally Congress outlawed tributyl tin. NAVC was defending it, and they'd say this is a military necessity, okay? But some of the, the oystermen or the clam diggers or the crab, I guess it gets the crab too. There was just nothing. If a Navy ship came in that harbor, gone. Okay, so that was back when I was working with David Taylor on a regular basis each summer. Sort of interesting to hear people talk about whether they should be using tributyl tin or not. Most of the civilians working at David Taylor thought we shouldn't be using it, but it was such a cost saver. Okay. Now, one person told me, one of the two ends told me once, if you just take a submarine up to the Arctic, you can freeze them off. Okay, or in the cold water, but I've never been able to confirm that. I don't know if he was pulling my leg or what, but anyway. But barnacles can be a problem. So what else do I want to say about soils and wet dry? So you have to worry about moisture, but you've got plenty of moisture in most cases. Actually, what we've been following, just for your information on some of this stuff, is basically this thing from the forms of corrosion. We talked about general attack earlier today, and we were talking about 0.002 to 0.010 of an inch for carbon steels, and we haven't talked about general attack, but general attack is just a general wasting, rusting everywhere. We talked about localized attack. We talked a little bit about pitting. Pitting is a wearing away of the surface locally, and you get corrosion at a pit. And one of the things I handed out on marine corrosion has a nice little picture of how you get acidic regions and basic regions right around the pit, and it sort of They sometimes call it autocatalytic, how that drives the pit. Okay, just boring a hole. And I've seen pits. I talked about the pits in my mother-in-law and the dinnerware. I also had a situation, actually my thesis advisor had a situation over 40 years ago. When copper prices went up in the early 1970s, the stainless steel industry thought they had a great solution to use stainless steel for piping in a home. Problem is you can't easily solder to stainless steel unless you use a very aggressive flux. And so they decided we would plate the outside of the stainless steel with copper. And that way they could solder to the copper. Okay, that sounded great. So it turns out in order to plate stainless steel, you got this stainless steel tube, and you want to, so this is iron chrome alloy, okay, and then you want to plate on a very, very thin layer of copper, and copper is noble to stainless steel. But whenever you plate something, you actually have what we call holidays. There'll be little pinholes, microscopic pinholes. And what happens there is now you get an acceleration, and you have this as your cathode, and your anode becomes your stainless steel right here, and all the area driving the electrons is focused right on this. And so they put this in a big condo, 40-story condo down in Florida. Turns out right on the ocean in Florida. Turns out they have salt in the air. They have hurricanes come by, and within about a year and a half, they had a sprinkler system in their building. But it wasn't intentionally a sprinkler system, it was the water piping system. And so my thesis advisor was involved in that. For me as an assistant professor, I was trying to feed my family on assistant professor salary, so he gave me some work at $15 an hour, which was typical technician pay back then. And I did some tests. I could take 100 ppm water, 100 ppm chloride water, and just stick it in this stuff with the copper on the outside, stick it in, and at the splash line where I had extra oxygen, I could perforate that. That was about 0.5 millimeter thick stainless steel, about 20,000 stainless steel. I could pit right through it in 24 hours in warm water. Okay, so it was great. You know, you could look up and see the stars if you put a flashlight in there. Okay, on the inside. So that's. I had another story. Oh, the other story on that, my thesis advisor. He used to do a lot of biomedical work, and anybody know what hydrocephalus is? You have a relative or anyone who has, it's water on the brain, okay? So certain people, they generate lots of fluid in the brain. It generates pressure, and it can damage the brain, sort of like a concussion, I guess. Anyway, so they actually will, they'll put a valve up here, and they'll run it down to your stomach, and it'll drain that excess fluid from the brain down into the stomach. I worked on a thing a few years ago with a design group here at MIT of students where they were looking at a valve so that they could implant this valve on top of the brain, and you could push a button if you felt the pressure, because you could feel the pressure if you had hydrocephalus. You could just push at one particular, open up the valve and drain it. So anyway, and they were having a corrosion problem, it turns out, but nonetheless. So this was in the early 1970s, so some MD decided he knew just as much about corrosion. Now this is actually a good story because none of you know enough about corrosion to go out there and become corrosion engineers after taking a few hours here. But this guy, he had read some textbook on corrosion, and he knew gold was really good, okay? I mean, I told you that the first day, right? Gold is very corrosion resistant. But if you put gold instead of copper here, gold is even more noble and could attack the stainless steel even quicker. And so he convinced one of the valve manufacturers for hydrocephalus to make a gold-plated valve. Okay, of course they couldn't put it in somebody until they got approval from the FDA and things like that. So they made it, and then my thesis advisor used to be Bob Rose, was consulting for this company. And when they called him up and said, well, this, and you have to understand the way medical devices and instruments are designed, usually some MD says, oh, this would be a great idea, okay? And the MD might know a lot about medicine, but they don't often know a lot about metallurgy or mechanics and things like that. But because they're the consultants being paid $1,500 an hour, and they hire some metallurgist at 1/3 or 1/4 that rate, and they don't treat them, the engineer, with the same respect as they do the medical doctor, because this person is a medical doctor, right? He knows everything. Anyway, so they called Bob up and they said, this famous doctor has this idea and he wants to gold coat the hydrocephalic shunts. They're called shunts, not valves. Anyway, because they shunt the fluid to the stomach. Anyway, and Bob says, not a good idea. They said, why not? And he says, well, if you put a noble metal on top of a non-noble metal and you concentrate all the corrosion current, focus it right there. And they said, well, you know, we have to meet with this doctor. We're going to have a meeting in 2 weeks in New York. Can you come? And so Bob says, yeah, but get me one of the valves ahead of time. So he doesn't get it until the Friday before. And what's he do? He takes the valve and he puts it in some saline solution, just regular old stuff they'd use in a hospital, right? Saline solution. Sticks it in the saline solution, puts it in his briefcase on Monday morning, and he goes to this conference room, and this doctor gets up and gives a half-hour presentation on galvanic corrosion, or on corrosion and electrochemistry, and Bob's sitting there listening to it, and this is why they should gold coat all these things. And at the end, they said, well, Professor Rose, what do you think about that? And Bob just reaches over to his briefcase. He pulls out this jar of saline solution, which is all black and murky because it's been corroding all weekend. Okay, he says, I put one of the shunts in saline solution on Friday. And he said everyone just sort of got sick and walked out of the room. And that was the end of that idea, okay? Which is not all that different than copper plating stainless steel, okay? Now, to talk about the protective layers on things like stainless steel, it turns out stainless steel has to have what we call a passive layer. Well, the passive layer is just the oxide layer, and people will often say it's Cr2O3. It's not really Cr2O3, chromium oxide on the top surface. It's actually something much more complex. It's Cr2OH3. But if you actually analyze the surface of a steel that has more than 10 or 12% chrome, that top surface of the steel will be almost 100% chromium. And chromium oxides, hydroxides, or whatever. It's not a nice simple crystal like Cr2O3. It's maybe an amorphous layer because it may only be 50 nanometers thick, but it imparts the corrosion resistance. The problem is, if you just get stainless steel off the steel mill, it hasn't had a time to oxidize any iron that might still be on the surface away, and it's what we call an active surface. And you have to put that stainless steel in an oxidizing solution like nitric acid. Nitric acid is an oxidizing acid, okay? It'll eat things up pretty well because it oxidizes things. You can put stainless steel in nitric acid and you can make stainless steel containers for nitric acid. But nitric acid will eat away all the free iron on the surface. So if you had any iron on the surface, it will dissolve away as iron nitrate, and you'll end up with pure chromium, and you go from an active surface to a passive surface. And passivity is an important thing in not just stainless steels, but lots of alloys, some of your nickel alloys, which have chromium and stuff in them. Sometimes people talk about passivity in terms of some of the brasses, okay? The Navy uses aluminum, manganese, bronze for propellers, and the aluminum forms a very protective aluminum oxide skin. Makes a passive surface. And as long as you don't break through that, don't get pitting, you can have a very good surface, okay, in terms of resisting corrosion. Well, I told you that they had to plate the stainless steel with, in order to put the copper on. The only way you can plate to a passive, you can't plate to a passive surface because you basically got a very thin layer of ceramic on the surface. And yes, you can get electric current through there and you could plate on there, but you won't get a metallurgical bond. You can take your fingernail and it will just flake off. The copper would just flake off, and that's not what you want. So you have to activate the surface. How do you activate the surface? You activate by putting in HCl. And in fact, that's what they do at the steel mill when they roll it. They have some oxide on there from high temperatures when they're rolling the stainless steel or whatever, hot forming it, and they pickle the surface. It's called pickling it in hydrochloric acid. The hydrochloric acid eats away the oxide. The black oxide that you don't really want, you get a nice shiny stainless, but now it's got some iron. There's still some iron on the surface. It's not pure chrome. So you take it and you put it in nitric acid at the steel mill, and you sell it as passivated stainless. Okay, but in order for the steel company, the stainless steel company, to make this copper plated tubing, they had to activate it in order to get the plating to adhere, which meant that when you now had the little holiday, you didn't have a passive surface. You just had, turns out, activated or active stainless steel will rust just like anything else. Okay? And how many times have I had someone come to me, this is supposed to be stainless, but it can't be, it's rusty. No, it can be. Okay? I can take stainless steel, I can put it in hydrochloric acid, and I can then put it in a saline solution and it will rust. And if you want to see this, go down to the New England Aquarium. Okay, the outside of the New England Aquarium has got these little plates that are supposed to look like great big fish scales. Okay, this is part of the design. And the specification was that they were supposed to use passivated stainless steel so that it would have marine corrosion protection. It's right there 20 yards from Boston Harbor. Okay? And they purchased passivated stainless steel sheet. They formed it, they stamped it and cut it into these big things. And then to give it a little texture, they took a grinder and they ground away little grinding marks on the surface. Well, what happens when you grind away the surface? You leave active stainless steel underneath the grinding marks. And so after about a year, you go over there and you look on the outside and you see right there in the grinding marks, a little rust just following the pits of the grinding marks. Okay? And so the aquarium brought me in and said, well, what do we do? I said, well, you were supposed to use passivated stainless steel. Well, we did purchase passivated stainless, or the manufacturer did. It was in the specification. I said, yeah, and then they ground it. And you could go over to where the food trucks, or the trucks deliver the food for the cafeteria, and see where they had actually run into some of these things. You know, the bumper hit it. Now you had a whole band this wide of rust, okay? Because now some stainless steel, if you activate it, if you're not right there in Boston Harbor with all the chlorides around, it might self-passivate over the next couple of weeks or months, just in the humidity of the air. You'll oxidize away the iron and you'll end up with a passive surface. But if you're there with chlorides right there, it won't always self-passivate. You need to do something. So we had to figure out some way. Were they going to have to take off all the facade of the New England Aquarium? It's going to cost a fortune. And then take it in, put it in some something to clean the rust off, and there are less aggressive things than HCl that you can clean the rust off, and then repassivate it. Or could we do it in place? Well, now the question becomes, if you do it in place, all the environmentalists are going to be worried if you start using nitric acid right next to Boston Harbor. All those little fish aren't used to drinking nitric acid. So it turns out in milder solutions than nitric acid that can passivate are citric acid and phosphoric acid. Okay, so we had little 1 square foot patches, and we had a little test program, and we have them rub on citric acid, navel jelly. Okay, I can't remember what navel jelly is made out of, but basically I think naval jelly actually has some nitric acid in it. Anyway, but naval jelly was something that you used to clean metal, right? We had tried naval jelly, we tried phosphoric acid, citric acid, we tried Coca-Cola, Diet Coke, okay? Why did you try Diet Coke? Coca-Cola is phosphoric acid, folks. And what would be better than telling the neighbors that we were cleaning it with Coca-Cola, because they spill Coke into the harbor all the time, right? And citric acid, well, it's just lemon juice, right? Which it is, sort of. Anyway, I think they ended up using the citric acid, and they did do it in place, but it's not as strong and it didn't work quite as well. But anyway, that's the story of the Boston Harbor and passivation of the stainless. But the passivation of the stainless is something that comes up all the time. In fact, most recently, I was looking at, last night, one of my co-workers gave me this, which is a scanning electron microscope photograph of a pit in, I put it away, but, oh no, I didn't. Remember I passed this around, which is a titanium pacemaker case? Well, this one's like 35 years old. But they still make them, sometimes they make them out of titanium, but the battery cases are actually made out of stainless. And a company was making these battery cases for 3 of the largest pacemaker companies, and they were having corrosion problems. They were having little pits. And you can see here, I copied this one, you can see the intergranular attack. This is the pit. You can see the oxides in the scanning electron microscope. They charge up and turn white. These are the grains of the stainless steel around over here. These are the grains of the stainless steel, but they probably had some chlorides. In fact, that's what everyone's pointing to, is where do the chlorides come from in the cleaning solution. But in fact, there's some data that says they're deionized water, which was supposed to be like 10 megohm or something like that. Well, their deionized water had a pH of 3. Okay? You have to actually change your deionized water sometime. Okay? And you're in the Coast Guard, right? You have to qualify ships. One of the first consulting jobs, when Quincy Shipyard was still in operation, I got a call because they were building some barges to transport. It was a crude oil, but it was a very heavy crude, and so they had to put some heating pipes in there so that they could heat it up to pump it back out of the barge. They can pump it into the barge when it was warm, but I guess maybe it's number 6 fuel oil. But number 6 fuel oil, if you just let it come to room temperature, it doesn't flow too well, and it doesn't pump very well. And so they basically they made these brass pipes, like 3-inch diameter, and ran them through the inside of the barge, and you could get there and you could run, it had Daltherm, which is a mineral oil type of heat transfer fluid, and they were finding these stress corrosion cracks in the brass. And they brought me in to figure out, we've raised everything properly, why do we have these stress corrosion cracks? The pH of their rinse water was 2.3. Okay? And it turns out this stuff that I just put up there, it's a similar problem. Okay? You don't change your rinse water. So if nothing else today, you learn that if you don't do maintenance on your fire protection systems, you get hardening of the arteries because you're introducing oxygen. If you don't change your rinse water, you're carrying over all those other stuff with the rinse water. And they decided afterwards that one way to solve the problem was to go from changing the rinse water once every 2 weeks or so until changing it every week. Now the best thing would actually be to monitor it every day, right? It's not too hard to measure the pH. And they actually knew how to measure the pH, but they didn't bother to do it. It's probably going to put them out of business. But anyway. Okay, so we have localized corrosion, which is crevice pitting, intergranular, local electrical difference caused by breaks in the coating or dissimilar metals. One of the dissimilar metals here is that we already talked about. They call it galvanic attack down here on this little thing. This is the noble metal next to the base metal. Well, this is just the copper on the stainless steel, or the gold on the stainless steel for the hydrocephalic shunt. Okay, so we're sort of walking through these things. We talked about the pitting. Crevice corrosion I actually mentioned yesterday when I talked about the silt that got in the titanium heat exchanger. It's also, if you look under, if you put under insulation corrosion, okay, if you've got some piping and you have a flood and the insulation gets wet, and the wet insulation creates this nice wet dry type of environment, okay, just like my roof out there in Arizona. And under insulation attack is a common problem. I had a problem. They were making Manwich down in Knoxville, Tennessee, you know, sloppy joes, right? And it turns out when you're making the stuff continuously, everything's fine, but when you stop for some reason, you actually have to keep that product above like 190 degrees Fahrenheit by the FDA standard so that you don't grow bacteria and stuff. Anyway, so they had this steam hot water tank, or this hot water tank that was supposed to be operating at like 210 degrees. I mean, the set point was 210 degrees. Now, you know, water boils at 212. Okay, but they wanted to get as much out of this tank as they could. And there's actually a nice little story in this. It turns out that the boiler and pressure vessel code requires that any pressure vessel more than like 100 gallons has to be built to the ASME code, which has all kinds of requirements for quality and wall thickness and everything else. But water heaters are exempted because people use water heaters for lots of things, or any vessel less than 100 gallons. So this was a 99-gallon vessel. People build a lot of 99-gallon vessels. If you looked at size of hot water tanks in the world, you see a big peak right here in the number of vessels that are 99 gallons. Okay? And that's because of the boiler and pressure vessel code, of whether you have to come under the code or not. So this tank was right there with all these others. It had been designed by this guy, and I think he had a year of trade school or something, you know. Nothing wrong with that, but so he's designing something that really should have been a boiler and pressure vessel. He puts insulation around it because it's a hot water tank, and of course they have to come in and disinfect. And what do they disinfect with whenever they're cleaning this food processing plant? But a nice chloride solution, right? And so they come in and they're spraying disinfectant every night, okay, to clean off the walkways and everything. And some of it gets underneath the insulation. 304 stainless steel, stress corrosion cracking. Okay, same thing as I showed you yesterday. Not quite as bad as this stuff. I'll pass this around, try to be gentle. Well, this one you don't have to be quite as gentle. The other one will actually fall apart if we're not careful. Well, actually, maybe I'll pass this around. There's another one that really is in tough shape, but you can see all the little cracks. And that's what basically happened to this vessel. The cracks didn't get all the way through. Unfortunately, they blew up one day, and someone was standing next to it, and they got scalded with 200-degree steam. Okay, because it's under insulation attack. Same thing as crevice corrosion. You'll actually get an acidic condition underneath the crevice and get preferential corrosion underneath something else on top of it. It can be dirt, okay, like I had a heat exchanger in a utility, and they made it out of Admiralty brass. We don't use Admiralty brass much anymore. We mostly use thin titanium tubes. But Admiralty brass, if you didn't have filters to keep the solids out of your heat exchanger tubes, and you get a little layer of film of that stuff, you just pit right through that Admiralty brass in about a year. Okay, so it's important to have filters. Okay, it's important to have to clean things. Okay, it's important to do maintenance to prevent the corrosion problems. Now there's velocity effects, is what he calls it over here, on corrosion. And one of the velocity effects is just erosion. And it turns out, if I look at copper alloys in particular are very susceptible to velocity effects. So here we've got copper, and this plot comes out of a book called Marine Corrosion, which I mentioned is out of print, by Francis Lequeux, okay? And Francis Lequeux was the corrosion engineer at International Nickel Company. And he later became senior lecturer at Scripps Institute of Oceanography. Turns out the International Nickel Research Center is named after Francis Lequeux now. And if you've ever seen corrosion data, and it comes from Curie Beach, North Carolina, there's two places where corrosion data, seawater corrosion data comes from. Curie Beach, North Carolina, which is the International Nickel site, okay? They own a piece of the beach in North Carolina. And the other is good old David Taylor, Annapolis, it used to be. And they talked about corrosion in Severn River water, okay? So right across from those of you that went to Naval Academy, you look across the Severn and you see this nice white old house, antebellum house. That's the David Taylor Research Center. And one of your classmates, Quirky Graham, once became head of that. And the commanding officer of David Taylor used to be able to live in that great big old antebellum house. Anyway, Severn River water was the Navy's facility. They shut down the Annapolis facility in the Bracks, and it all got moved to Carderock outside the Beltway in Washington. Anyway, the probability of attack in velocity in feet per second on copper's got a fairly soft oxide. It's a protective oxide, just like the protective films on other things. But in all water, we have some total dissolved solids, okay? Microscopic solids, and at certain velocities, those solids in the water going by will just eat away that oxide skin, just erode it away, just abrasive. If you use Admiralty brass, you can get considerably higher velocities. Aluminum brass, you get a very tenacious aluminum oxide skin. If you want something even better, you go to cupronickel alloy.